Hi everyone, I'm Sharwin Kumar from University Malaysia Pahang. First of all, thanks for the ISETs for giving me this opportunity to present my research about enhanced oil palm waste properties through torrefication and pelletization. First of all, this is my presentation outline. So I will talk about the introduction, experimental, results and discussion, and lastly conclusion. For my introduction part, the main idea of my research came from the availability of oil palm waste in Malaysia. As we know, Malaysia is second largest producer of oil palm waste. This oil palm waste can be converted to biopellets, where later it can be used to replace coal in power generation unit. In my study, the raw oil palm waste undergo torrefication process become biochar. This biochar undergo pelletization process to become biopellets. Currently, oil palm waste directly burning in palm oil mill and some of them just left over in plantation. Both of these scenarios cause environmental pollution like undesirable ash, carbon dioxide, carbon monoxide and global warming. This oil palm waste can be converted into biopellets. However, we have to torrefy the oil palm waste since they have some poor qualities like high moisture content, low energy density and they behave more hygroscopic. Each type of oil palm waste have their own composition of cellulose, hemicellulose, lignin, extractives, and ash as we can see in table 1. My purpose of research is to study the optimum condition for pelletization of torrefied oil palm waste and their characteristic of torrefied pellet produced. So for my torrefication of oil palm frond, palm kernel shell, and oil palm mazuka fiber conducted at 270 degrees Celsius for 30 minutes. And the pelletization of torrefied biomass performed at different temperature 110, 130 and 150 degrees Celsius and different pressure 10, 12 and 14 MPa based on the previous study. And there will be several analyses like mass yield, eye eating value, FTIR, density testing, moisture absorption and pellet strength testing. In my experimental, the biomass I chose were oil palm mazuka fiber (OPMF), oil palm frond (OPF), and palm kernel shell (PKS). I used nitrogen gas in my torrefication and carboxymethylcellulose as a binding agent in my pelletization process. For torrefication, the temperature at 270 degrees Celsius for 30 minutes. In pelletization, the pressure at 10 MPa, 12 MPa and 14 MPa and the temperature at 110 degrees Celsius, 130 degrees Celsius and 150 degrees Celsius for 20 minutes. This is my characterization of pellet. Next, the results and discussion. For first part, the mass and energy yield. From the figure, it clearly shows that PKS have high mass yield because of its lower content of hemicellulose compared to other biomass PMF and OPF. PKS also gives higher energy yield because PKS have higher amount of carbon content compared to other biomasses. So the higher carbon content is resulted higher eating value which it contributed to higher energy yield. The next part, the high eating value. For the high eating value, the torrefied pellets are much more higher compared to the raw pellets. During torrefication, the carbonization process occurs, which is convert the biomass to the carbon. The eating value of torrefied PK is also much more higher compared to the other biomasses due to the carbon content. For the ultimate and proximate analysis, PKS have higher fixed carbon compared to OPF and PMF, which enhance its eating value. The carbon content in PKS mainly contributed by lignin itself, where lignin consists 49.83% of carbon. The oxygen content of raw PMF and OPF were higher than PKS, which is resulting lower mass yield in PMF and OPF. The ash content of PMF also higher than PKS and OPF. Next, the FTIR. So as we can see, the region 1 until the region 5 it represents the composition of the hemicellulose, cellulose and lignin. So there is a much more difference compared to the raw biomass with the torrefied biomass. Next, for pellet density. From the figure, the torrefied pellet have higher density than raw pellet because of its brittle characteristic. High lignin content in PKS make the pellet more brittle and have high density compared to the other biomass. Next, the pellet strength. The suitable die temperature and pressure were under 30 degrees Celsius and 12 MPa. At under 10 degrees Celsius, the pellet could not be formed because of the insufficient heat supply, and at 150 degrees Celsius, the biomass can be like a more brittle because of the high temperature, so it like break easily during pelletization process. For the pressure, the pellets have a low strength at 10 MPa and 14 MPa because at 10 MPa it does not get enough compression force, and at 14 MPa it like a over compressed so that the pellets are not strong enough. For the moisture absorption rate, the torrefied biomass have a lower moisture absorption rate compared to the raw biomass due to the degradation of hemicellulose, which cause the loss of hydroxyl group. For my conclusion, the optimum condition of pelletization at 130 degrees Celsius and 12 MPa. These torrefied pellets have some benefits such as better eye heating value, low moisture absorption rate, and better pellet strength compared to raw pellets. So these torrefied pellets have potential to replace the coal in combustion units, thermal power plants, and electricity generation. This is my list of references, and that's all from me. Thank you.